So welcome. This is our 18th meetup. It's been a long way, certainly.
And our second one here.
Yeah, a second one here at Facebook, which is amazing.
So thank you for Facebook for hosting it.
So if you want to use the competition for anything, you can use Twitter as well, or Facebook. It's up to you.
Don't use Twitter.
We won't force you to use anything you don't like.
We do have a Facebook page now.
Yeah.
We're live streaming on the Facebook page. So if you're not here, then you can watch it on the live stream later.
Yeah, so put the hashtag London DevOps so we can see it, and we know who you are, we know where you live now. So we have a code of conduct as any self-respecting meetup and conference. It's basically be nice to each other, talk about the weather, that kind of thing, ask how your day has been, stuff like that. We are, I would say, incredibly happy. For this meetup, we passed the 3,000 members.
Well, hey. Hooray.
Yay.
Can you remember who our 3,000th member was?
Actually, I do. I can't remember his name now, though. So,
Anybody know who the 3,000th member was? It was a guy called Barry. Barry Leonard, did you hear?
yeah.
Oh, hey,
Yay.
cool.
Member number 3,000. So come meet me after, and I have some stuff for you.
Well done, Barry. 3,000th member. Yay.
Yay. So as you can see, we're getting slightly cramped now.
No, I'm not doing a very good job of advancing these slides.
It's all right. So again, we wouldn't be here without the generosity of our sponsors, especially Yonder and Beyond and Prism Digital. So Prism Digital, Yonder and Beyond guys, say hello to everyone. So yeah, there you go, just over there. Jack?
Hey guys, I'm Jack from Prism Digital. For those who don't know me, for my sins, just wanted to say a quick hello. So what we do, we're mainly focused around DevOps recruitment. So I won't bore you with that. I'll let the talks get on. But one small thing, my colleague Sam Galvin, that guy over there, right at the back, asked his girlfriend to marry him last night. So one big cheer for Sam Galvin. Hey.
Did she say yes, Sam? Oh, thank God for that.
So
okay.
We're also here thanks to the generosity of O'Reilly. So if you got some of the swag on the back, and DevOps guys as well, which is a DevOps consultancy, which is a direct competitor of this guy here.
No, not those guys. Where's my slide gone?
I don't know.
Is it later?
After this, yeah.
After this, is it? Okay.
Oh.
We'll do the Facebook slide.
The timing wasn't good. But as said, and we're here thanks to the generosity of Facebook. And I would like to give the biggest round of applause to everyone at Facebook who helped organize this, to Paulo, to Rodrigo, to Mohit,
Joe.
to Joe as well.
And everyone.
Everyone, you guys have been amazing so far. It's incredible. It's a pleasure to be here. So we would like to invite Paulo, who's one of the engineering managers here at Facebook, to talk a little bit about what they do, just in case you don't know. So go ahead, Paulo. Big round of applause, please.
Hello, everyone. I'm really super happy to have you here tonight. So my name is Paulo. I'm a production engineering manager at Facebook. You might be wondering what production engineering is, actually. So to put it in a simple way, we are the reason why DevOps is possible at Facebook, and we are the reason why it's possible at scale. So production engineers at Facebook, they are a mix between software engineers, system engineers, network engineers. So as you can see, they have a very unique set of skills. They build the tools, so software engineers can actually operate their services. And so they can operate their services at scales. Tonight you will be having two talks from Facebook production engineers. Those are stuff that we're doing in Europe. And I hope you will be getting an overview of what production engineer is at Facebook and why it's so unique in the industry. Ask plenty of questions, please. There is a mic here. Everyone asking a question will get a Facebook T-shirt. So you have no excuse not to be asking questions. Again, I'm super happy to have you here. There are a couple of Facebook engineers in the room, so if you have questions after the meetup, just reach out to them and ask questions. Thank you.
Cool. Thanks, Paulo.
Perfect. So just in case you don't know us, this is a photo of the 4 organizers. So there's Marta here, me, Mark, Jack, who was around here just 1 minute ago and disappeared suddenly.
He's around somewhere, don't worry about
He's
him.
somewhere around. And Mireia, who's over there. So any question, anything, if anything you like or dislike, just let us know.
Cool. There's my slide. Hey.
It
Cool.
eventually appeared.
Yeah, so final sponsor is Contino. It's a company that used to be called Contino, and then was then called Sendachi, and is now called Contino, and probably be called something different next week. If you want to come and work with me, doing that sort of stuff, which looks like some computer game from the 1980s called Cuba, I think. Well, that's what we do. If you want to work with me and you can tolerate working with me, then come and talk to me afterwards. Or Reese, we can recruit a dude just down there.
All right, so as we always say, we're here for the community, as part of the community as well. And the thing that we really like to do is to tell you to go to the meetups as well. So these are the meetups that we found that might be interesting between now and the next meetup we have, which is in 2 weeks. So there's not much this time, I'm afraid. So we have the Jam inaugural meetup. So you know that we had a talk about Jenkins on our last meetup. So the Jenkins AM, which I don't know what it stands for, to be honest, the user group of sorts, it just started their meetup. So they're doing the initial one at Google Campus. And then we have DevOps Playground.
DevOps Playground, Andy Curitan's meetup on the day after that, over at Forest down in Bermondsey.
Yeah, and of course we have Infracoders London, which is one of the oldest meetups about automation that's been running for 4 years now. I think it's been going for a long time, which is being hosted at CodeNote.
Cool, and then the Prometheus London user group, so Prometheus new monitoring tool, they've started up a London user group, being run by Matt Bostock, great guy. Go along to TBA, wherever that is, on the 8th of July, and see lots of good monitoring stuff.
Okay. So we have upcoming conferences. There's one that I forgot. It's kind of important, HashiConf. I apologize because I forgot to add it. So HashiConf is in Amsterdam, I think, next week.
Yeah, it's next week, 14th, I think.
It's very good to go there and meet Mitchell Hashimoto, who's an amazing guy, by the way, and tell him I told him to pay drinks and stuff. He'll be, yeah, you know. So we have DevOpsCon in Berlin. We have a 15% discount if you want to go there. And just for the excuse to go to Berlin and enjoy the city is just worth going, certainly.
Cool, and then Cloud and DevOps World is in 2 weeks' time, so that's over at Olympia, and we've got our meetup in the evening after that. So if you fancy going along to Cloud and DevOps World Forum and staying along in the evening, then we'll be there to do another meetup. And you know, vice versa. If you want to come to the meetup, then go to the conference a bit early. You might learn some new stuff.
So that's pretty much everything for us. So the 3 talks we have today, first of all, we have Mark Drayton from Facebook, who will be talking about getting Gits from developers to users. So it's a very good talk. Then after that, we have Mateusz. Did I say that right? Yeah, Mateusz? Perfect. So Mateusz will be talking about continuous integrating in the data center provisioning space. I've seen him rehearse these. It's a very good talk.
And the last one from Elton, who's going to talk about IoT and Docker. So 2 of the biggest buzzwords in the industry. He's got a really, really good story to tell on that. So looking forward to that quite a lot. That's the last of the slides, isn't it, Mark?
Yep, that's it. So enjoy the talks, and first of all, Mark.
Yep. So Mark's coming up. So we'll do the talk. Please don't shout out questions during the talk because we won't be able to hear you properly. We're going to line up at the microphone if you've got questions after the talk. But here he is, Mark Drayton.
Yep.
Okay, hi. So thanks for coming. My name is Mark Drayton. I'm a production engineer in the Web Foundation team here in London. So the Web Foundation team, its responsibility is the performance and the reliability of the site as a whole. So anytime there's any kind of serious problem with Facebook, or it's slow, or anything else is going wrong, we're the team who look into it. Consequently, we have a lot of a broad understanding how much of the stack works. So today, I'm going to talk about how we ship Facebook.com. Okay, so what exactly do I mean by shipping Facebook.com? So as you might imagine, the broad architecture of Facebook is that users first land on a load balancer. From the load balancer, we send the user's request to one of our pools of web servers. So we have web servers distributed across the world. The web server, takes the request, and it starts talking to the backend services that are needed to assemble the page. So we have databases and caches and other services. In this talk, I'm going to focus on the code that runs on the web tier itself. So this is the PHP code that product engineers write. We ship this code at the moment 3 times a day. This is very important. Shipping code very often is really good for users, and it's really good for engineers as well. And I'll cover why that is throughout this talk. OK. So, a quick overview of what I'll talk about. So I'm going to go through how our developers interact with our code base, how we build and deploy a release, and then what we do after it's gone out to make sure that things are OK. So first up, our development model. What does being an engineer at Facebook look like, or being a product engineer at Facebook look like? So all of our code is in a single code base. We don't have a separate code base for newsfeed and another code base for friends or whatever it is. We have one big monolithic code base. We access this using Mercurial, and it's always been this way. We've always had one code base. We've had different version control systems, but it's one code base. And the main reason why we have a single code base is because it makes it really easy for us to make sweeping changes across all of our code. If we develop a new API, which is much more efficient, we can make a single commit and change every call site to use the new API and suddenly become more efficient or more flexible. So we can do things like this. We can replace every call site for get friends with await gen friends to make this code that was previously synchronous become asynchronous just overnight in one hit. So this is really cool. OK, but this, I want to talk about how engineers actually interact with this code base. So if you're a PHP engineer at Facebook, you're working on newsfeed or something, this is what you do to make changes. So you check out the code locally. Every engineer has a development server, which runs essentially a production web server. So it's running the same PHP code we would run in production, and it's engineers can make changes and test them out and iterate on their code in real time. We have access to the same backend services and test users and everything that's necessary to get the full Facebook experience on your development server. So if you're making a new feature, you would iterate locally, go backwards and forwards until you're happy with it, and then you make a diff. So a diff is a proposal for changes, code changes. The diff goes to your peers for review, so they get to check your code to make sure that you're not doing something that's going to break or cause problems in other ways. And once the diff is produced, we asynchronously run a bunch of tests. So we run the complete test suite against the new code, and we also have a tool called perflab that runs against your new code. So perflab is a performance testing suite. So we build the current release, we apply the diff you've made to the release, and then we replay a bunch of traffic against the code to make sure that there are no regressions in it's not using more CPU than it should, it's not using more memory than it should, it hasn't introduced more errors, or it's not making the site slower. Basically a battery of tests to give us some confidence that this change is going to be OK. After that, we go to the code review stage. So your peers are looking at the diff, they're making sure it's OK. Sometimes they might request changes, and we'll go around this circle a few times, changing things to make sure that they're OK. And then finally, once you're happy with the code, you commit it. So what actually happens when you commit code? So I mentioned earlier that we have a single code base. Well, within that code base, we basically have a single branch as well. So we have trunk, and trunk looks like this. It just goes on throughout time. So engineers, they make changes to the code, they commit to trunk. So we have Alice committing some code, and we have Bob, and then we have Craig committing code. And these commits are just going on through the future. How do we get this into production? So first of all, we don't just push this thing directly. Instead, we cut a release branch once a week. So we have day N. 1 day a week, we make a new branch. And then 2 days later, we first push this branch to production. So we have this 2-day period. And the reason why we have 2 days in between is because we want to have plenty of time for this code to be tested by employees. So at Facebook, we don't really have kind of a dedicated QA department. Instead, we, because this is pretty slow, it takes a long time to get code QA'd and all the rest of it. So we rely on automation for a lot of this stuff, and we also rely heavily on employee testing. So The weekly release, as this first weekly push is called, is tested for a couple of days by employees before it goes out. And then after that, after we have the weekly release in production, we make daily changes to it. So several times a day, we will merge code into this branch, rebuild it, and then push it out again. So what does this look like for engineers? So our engineers here, Alice, Bob, and Craig, when will their code go out? So Alice committed her code to trunk before we cut the release branch. So her code is going to go to production the next time we push the weekly push. Bob and Craig missed the branch cut. So if they do nothing else, their code will go to production the week after Alice's. But what if Craig wants his code to go into production sooner? In this case, we can merge the code from the trunk branch into release and push it with one of the daily pushes. And I'll come on to exactly how that works in a few slides' time. So first up, this model has some consequences. Having a single branch has some impact on the way we do things. First of all, there is the implicit statement that by committing code to trunk means you're saying this thing is good to go, because this code will go to production the next time we cut a weekly branch if you don't do anything. So this is not something where we can commit code and then iterate on it, and then someone later will merge the branch together and it will go to production. This code is going to go to production. Second up, we don't have feature branches. If we're developing a new version of Newsfeed, we don't do this in a separate branch and then test it and merge it, as I just said. So we have to gate all of our features in code. So we have this pretty sophisticated feature gating system. So the way this works is we can break down our user base into individual sets of users and then roll out new features to those users progressively. So the configuration could look something like this. Here we're defining that we want to build a group of users which contains 1% of, say, Brazilian users. And then in our code, we can do something like this. So we say, if you match this group, if you're in this 1% of users, then run the new code, otherwise run the old code. And then over time, we would dial up the number of users, we'd expand it to more countries, and then eventually we would get to the point where this code is live and we can remove this check in our PHP. Another interesting aspect of this, which we had to think about, was that we don't want the same small set of users to receive all of the experiments. If we were testing, say, 5 different features on 1% of Brazilian users, we probably don't want those same five groups to land on the same users. Otherwise, they might get a sort of really inconsistent or weird experience. So we salt the groups to make sure that we pick different sets of users every time, consistently. OK. So next up, what are the other consequences? So the last consequence I already mentioned is that employees have to do a lot of our QA. Again, this is so we can deploy things faster. We rely really heavily on having employees detect serious problems for us. OK, so that was how developers interact with the code base. How do we actually build and deploy a release? So, this is the push process, how we build and deploy a release. So pushing code. Every day, I mentioned that every day we do up to 3 code releases. So each one of these code releases has several steps. Broadly speaking, they are building the release, so that's merging the code together, testing it, making sure it's actually going to work, and then getting it out of the door as soon as we can. So who's involved in this process? So first up, we have the engineers. They've been beavering away, making new features, fixing bugs, all the rest of it, and they're eager to get their code out. Secondly, we have the pusher. So this person is someone who works for release engineering. Their job is something like a conductor in an orchestra, or I don't know, a mission controller or something. They are making sure that all of these changes work together and that we end up with a viable release that's going to work in production. They're coordinating the entire process. And then last of all, we have a lot of automation. We rely very heavily on automation. The process of merging changes between the 2 branches is fully automated. The process of deploying to the site is fully automated. We just press a button and this thing goes out of the door. Without this automation, we couldn't do this 3 times a day. So what does this look like? What does the push process look like from an engineer's perspective? So I mentioned that we have to merge the code from the trunk branch to the release branch. So if you remember Craig a few slides ago, he'd committed to the trunk branch, but he had missed the branch cut. So at this point, his code would be merged into the release branch. So this doesn't happen automatically. And an engineer cannot choose to do this. Craig cannot press a button and commit into the release branch. Instead, he requests a merge. So he says, I want to push this code into production. And by requesting a merge, he's he's promising that he'll be around to support this code, to make sure that it actually works. So first step is request a merge by visiting some internal tool to do this. And then secondly, he's committing to be available. So the push process is managed entirely on IRC. We coordinate everything on IRC. We have bots that announce the progress of the push. They will ensure that people are around to support their code when they've actually said they will be. And engineers have to be available to test and fix any issues that come up during the push. And then essentially what we're saying here is engineers have to be responsible for their code. We've chosen to avoid having a QA department and an operations department whose responsibility is building some code and getting it out of the door. Instead, we're kind of devolving the responsibility to the engineers themselves by making them participate in this process. If you're not around to support your changes and be responsible for them, then they won't go. They won't go out of the door. Okay, so quickly, let's talk about what the push process itself actually looks like. So first of all, we have to merge and compile the PHP. This is merging the proposed changes from the trunk branch into the production branch, and then compiling the PHP. So the web server that we use is called HHVM. So this is a just-in-time compiler. It's a just-in-time runtime for PHP. So there are a couple of steps to how we actually use this. First of all, we compile the PHP into bytecode, into a big blob. And then we send this off to the web server, and the web server actually turns this into machine code on demand. So that's the bytecode itself. And then secondly, we also need to build static resources. So it's very common for a change to the product code to have some JavaScript or CSS that needs to go with it. So we also build a big bundle of static resources as well. After that, we ship them to a few internal hosts. So we have just a few hosts that engineers can do a very basic sanity check on, just to make sure that their code actually does what they expect it to do. After that, we send it to a small slice of production. So we actually put user traffic onto these machines, onto this new release, to make sure that it's working okay. At this point, the pusher is paying very close attention to the key system metrics. Are people still able to comment? Are they still able to like things? Is CPU utilization okay? Are we leaking memory? All of these kind of things we pay close attention to. But probably the strongest signal we have of whether things are okay or not is looking at the error logs. So it's not feasible to look at the error logs from thousands and thousands of machines. So we have a system called LogView, which watches all of the error logs from all of the web servers, normalizes the messages, so we strip out things like user IDs and so on, and then collapses them into an in-memory database. So we can make graphs like this. We can look at the rate at which individual error messages are firing and see if something has changed at the point where we push the new code. So we can see here that the blue line and the red line jumped up as soon as we got to phase 2 of our deployment. So at this point, the pusher would start looking at these error messages, and he would figure out how serious they are. Like, is this a serious bug that can't go to production, or is this just some noise in the logs? He would talk to the engineers and so on. And then we'd go back to our push process. So we have a couple of options here. If we find some problems with the new release, we can either turn off the code. Maybe there's a kill switch where we can just prevent this code from running in the first place. We can fix it forward, which means we commit a fix to fix whatever is broken in the new release, or we can just revert the change. So we can just unmerge the code that we merged into the release branch earlier. So it's pretty common for the push process to go around a few times before we land on a build that we're actually happy with. Okay, so once we have a build that we're happy with, we need to get it into production as soon as possible by deploying it to all of the hosts. So the speed that we deploy at is kind of a trade-off. So we want to get the build out as soon as possible, because having 2 builds live at the same time is kind of a bad, potentially a bad experience for users. They could bounce between the old version of the site and the new version of the site. So we try to minimize the overlap period. But on the other hand, if we try to push faster by taking down more of our capacity at once, then we don't have enough capacity to serve the rest of the traffic. So I want to quickly go over the restart process for a web server, because it takes a few minutes, and then some optimizations we made to make this faster. So how does restarting a web server look? Fairly straightforward. We download the new packages, so the bytecode and the static resources I mentioned earlier. We stop the old web server process. We start the new process. we have to prime some caches. So a lot of the information that we need to run the site is very hot. Things like configuration data. We need to have this stuff in memory before the web server starts. So we copy this data into memory. Then we preload the we preload the bytecode, so it's ready for the JIT when it needs it. And then last of all, we warm up the JIT. So HHVM's performance is actually very dependent on the order in which it compiles the code. So we have a few warm-up requests which run very hot code so that it all gets located in memory, very tightly packed in memory. This makes things a lot more efficient. And then after we're done warming up the JIT, we can return user traffic. So if we look at a graph of how the push process looks, it's something like this. So we take down some chunk of the traffic, and then a few minutes later, that chunk of the traffic has restarted, some chunk of the web servers. And a few minutes later, those web servers have recovered, and they're back up to full strength again. And then we take another wave down, and so on. So the number of waves we have in our graph is a function of how much capacity we're taking down each time. So if we want to make the site push faster, one option is to take down more capacity. So in effect, we just make these drops larger. But that's no good, as I mentioned. We don't have enough capacity now to serve the rest of the site. So this became a kind of a problem this year. So we did a lot of optimization to make it possible to restart the site faster. So some of the optimizations we made, so instead of downloading the packages ahead of time, we now download them concurrently. So during phase 2, when we push the new builds to a small fraction of production servers, we also send this kind of prospective build to all of our servers, so that when they eventually restart on this code, it's ready and waiting for them. This is actually kind of complicated because it turns out that writing a lot of data to the disk while the server is running can be pretty disruptive. You end up thrashing the page cache and so on. So we do things like use direct I/O, we use squashfs to try and minimize the disk I/O at this point. So that helps us save some time. Next up, instead of copying the cache that we need to run the server into memory, we just map it into memory now. So we map it directly into the processor's address space so that we can save the step of copying it directly. So yeah. Okay, and instead of preloading the bytecode, we lazily load it now. So this is something that for a long time we thought we wouldn't be able to do. We thought that things would be too slow if we tried to lazy load the code. But it turns out that actually this works fine. So not only is this faster, we also save memory because we don't load code that we actually never execute. There is a lot of code on Facebook.com, and a given server may not execute all of it. So there's no need to have it all in memory. Okay, so what does this actually achieve at the end of the day? So now the push process looks more like this. So we have each of our little waves takes less time. So if we want to push in the same amount of time, we can just have more waves. So we take down a smaller amount of traffic at each time. And the push takes the same amount of time that it used to, but we have more capacity available at any given point in time. Alternatively, if we really need to, we could take down more capacity and get the site out of the door faster. So we have some more flexibility because of this work. Okay, last up in the push process itself, we have a bunch of safety nets in place. So we have automatic, well, the push process will abort automatically if the site's latency or error rate increases seriously. We try to avoid shipping bugs, but now and then we ship something that could risk taking the site down. So we have these early warning mechanisms that will stop the site if things start to get, sorry, it will stop the push if things start to get slow or have more errors. And lastly, the pusher himself or herself and the Web Foundation team pay close attention to the site as we push it. Okay, so after the push, how do we tell whether things are okay or not? How do we make sure that we haven't pushed a regression? So first of all, we pay attention to some high-level metrics. So things like the HTTP 500 rate. If we're serving more HTTP 500s, then these are this is bad for users. These are fatal errors. It means we failed to serve the pages in some way. We watch the 99th percentile latency. If our slowest requests get even slower or we have more of them, then this usually indicates that something is seriously wrong. We watch the CPU utilization. So CPU is a resource that is pretty scarce, so we have to be really, really careful that we haven't pushed code that uses more CPU. We watch the number of error logs, the number of error lines we're logging per request. Generally speaking, if the logs contain more noise or more data, then this usually means that something is wrong and we might need to investigate what's going on. And then last of all, we pay attention to the number of requests that exceed the time or memory limits we have in place. Requests can't take an infinite amount of time here because we risk monopolizing all of the threads in the web server. So we have a hard deadline after which if a request takes that long, we'll kill it preemptively. Okay, so last of all, I want to quickly walk over a tool that we use for detecting CPU regressions. It's called Xenon. So here are some hypothetical made-up PHP code. It takes a user object and returns a list of that user's friends of friends. So how would we tell if this code is suddenly less efficient, using more CPU or whatever it may be? So we have our tool called Xenon. So Xenon periodically collects backtraces of the running code in production. So it will look at what's on the CPU and record a stack trace of how we got to that point. So it will produce samples that look something like this. We have the request we were serving and then the PHP backtrace of how we got there. So in this case, we're doing something like handling a request, fetching a user, trying to render their newsfeed, which in turn means we have to fetch their friends of friends. So we take these backtraces, we send them to our monitoring system, and then this lets us do things like show the percentage of backtraces that contain code that went through get friends of friends. So now if we see an increase here, this means one of two things. Either we're calling get friends of friends more frequently, or it's using more CPU because we see more of it. So Xenon's awesome. This is an open source extension to HHVM, and this allows us to track CPU regressions down to tenths or hundredths of %. So it's really worth using. Okay, so that's basically the end of my what happens after the push. So in conclusion, I want to go over a few things that we've learned during 10 or so years of pushing Facebook.com every single day. So first up, pushing often is great for users and it's great for engineers. It's great for users because bug fixes and new features go out sooner. It's great for engineers because it allows them to iterate much faster. Keeping the process simple really helps. Having a single code base, a single branch, a well-defined process really helps helps engineers understand where they are and what to do. Automation is essential for scaling. If we didn't have heavy automation around merging code, deploying the release, checking to make sure that things aren't breaking when we push, automated testing, performance analysis, we wouldn't be able to do this as often as we do. And then last of all, and perhaps most importantly, by making engineers responsible for shipping their code, we can make the process faster by devolving the responsibility of QA to everybody. So that's it. Any questions? Many questions.
We come to the mic, folks. Come on, who's going to come to the mic first? Go on, Mr. Hardy.
You chose the branching model of a branch per release, as opposed to a tagged release from master. Mm-hmm. Why?
That is a good question. I'm actually not sure. I mean, this model predates me. This has been around for a long time. I assume it's because it makes it easy to move code in and out of the release branch, but I'm not actually sure, I'm afraid.
I asked this because I'm having this battle at the day job.
Oh, really? Okay.
Well,
or maybe we can talk afterwards.
Come to the mic, guys. Come to the mic.
Hi, thanks for talk. I have a question. How long it takes to deploy one server? Because when I've tried HHVM, it's like it's fast when it's compiled, but when it's actually compiled, your stuff it's pretty slow, very slow.
Right. So it takes something like, I don't know, on the order of 5-ish minutes to restart one of our web servers. We restart the server, we warm up the JIT, and then it's taking traffic again in around 5 minutes.
So like a complete deployment, complete compile, take 5 minutes, something.
Oh, sorry, that's how long the web server itself takes to restart. If we're talking about the compiling the bytecode stage, then this takes much longer. This is tens of minutes or maybe even an hour.
Okay, got it. Thanks.
Come this way and get a t-shirt. Cool. Next.
Hi, I was so your feature gating sounds similar to feature toggling. I was wondering how you manage this. So how you manage them. First, your tech debt, when it comes down, how you get rid of the ifs, and do you just have a load of ifs in your code, or what do you? How often is it?
So I think we have, as far as I remember, we have some systems which try to detect old, unused rollout configurations and reap them after an amount of time. But basically, more or less, yes, we do have a bunch of ifs in our code base. It's actually, the API is a lot more elegant than just a basic if statement, but yes, I mean, unfortunately, that's a side effect of this model. We do end up with a bunch of branches.
So, like, how much tech debt would you actually have after, like, say, a release? Would it automatically be taken care of, or do you have to manually go and remove all those ifs?
So, as far as I know, there's nothing that does it automatically. So it probably happens naturally. Our code base changes very, very frequently. Like our APIs move a lot. You know, we do a lot of refactoring. One of the benefits of having this big code base is it's easy to refactor. So a lot of code gets reaped as a sort of natural process anyway. So I think that's probably where most of it goes.
All right, thanks.
Well, great, thank you. Who's next?
Hi, thanks for the talk. Yeah, you mentioned about unmerging when a problem sometimes happens.
Yep.
Do you unmerge the particular commit, or you unmerge all the commits at that point of time if a problem has occurred?
We unmerge. Sorry, please carry on.
And how do you, I mean, is that automated, or is that the responsibility of the developer at that point of time tracking QA?
Okay, so the question is, how do we unmerge things? So yes, this is automated. The pusher can just click a button and unmerge this request. And yes, we just unmerge that particular request and anything that it depends on. Well, anything that depends on it. So we have a way of tracking dependencies, and we can automatically unmerge things that depend on whatever we're getting rid of.
Okay, thanks. I would probably like to know more about that.
Sure, thank you.
Talk later.
Who's next?
Hi, just a simple question.
Sure.
What do you use to monitor your metrics?
Oh,
Is it open sourced?
Sorry, what's that?
Is it open sourced?
What do we use to monitor our metrics? Most of it's made in-house, unfortunately. We do use Nagios for some things. Nagios is a great way to execute a bunch of commands in parallel, so we use it for that.
All the time series data.
Yeah, the time series data is something we've developed in-house. Yeah. We can talk later. Maybe there's some things we've written on the internet about this.
Oh,
Okay.
Thanks.
Hi, thanks for the talk. So you have 3 opportunities to push to production per day, and so if someone merges something and it gets pushed and it gets messed up, is that pretty much the only opportunity on that day for them to do it? I mean, is this 3 pushes spread out over 24 hours or across all your offices?
Yeah. So the question is, if something bad goes out, how do we get it back, basically, or how do we get rid of it? Is that?
I mean, is there only one opportunity per day for someone to in their time zone realistically push and fix something?
More or less, yes. So we push once during the London time zone and twice during the California working day. Although in practice, this means that it's pretty. If you're an engineer in London, it's pretty easy to make the early morning push in California. If something really serious had gone out, then we can hotfix the deployment and fix anything outside of the regular push schedule.
Cool. Thanks.
Okay.
Well, we've only got a couple of minutes left, so please don't join the queue anymore.
How long do you keep your versioned API, your older versions of your API for? How much extra work does it give you to maintain that if you're always moving forward with new versions of your API?
So are you referring to the slide I showed where we could change one API to a new API?
Yeah.
We don't keep the old ones. We just move the code base wholesale from one to the other.
Okay, so how do you make sure your old stuff doesn't break, or you just say die?
No, we have a bunch of tools which make it easy to mutate code. We have tools that can just take the entire code base and change one call site to a different call site.
Okay.
Well, thank you.
Hi, great talk.
Thanks.
Just how do you manage all the number of engineers and the code? And you're pretty big. You've got multiple countries. Is there an overall strategy in terms of hierarchical? Oh, these are the guys who control pretty much everyone, and someone has their overall say at the top, or is it all very, very tiny little changes, so you're not actually noticing a management issue of code and people and stuff?
Okay, so you're talking about code ownership?
Yeah.
Okay. So nobody really owns anything at Facebook. It's okay if I find a better way of doing something, I can just make a change and will probably be okay. But that said, there are teams who are responsible for different areas. So we have teams who are responsible for the APIs which fetch data from the cache. We have teams who look after, I don't know, the database APIs, teams who look after whatever else it may be.
Right.
And then there are product teams within that. So the newsfeed team, the photos team, and so on. There is no rigid structure, though.
Yeah, okay. So
it's pretty
it's
fluid.
spread, but you still manage to make a more smooth flow of
Yes,
everything.
exactly, yeah.
Cool, thank you. And sorry, we're just about out of time, so talk quickly, Pete.
How do you distribute or how do you bundle up the binary/static data, and how do you get it out really quickly to all those servers?
It's bundled up into, basically a tarball. And we use BitTorrent for copying it out. I mean, we actually use SquashFS for mounting it, but...
Hi. What's a lazy load? You're talking about
Right. What is lazy load? So I mentioned initially we would preload the bytecode into memory. So, sorry, into the server. So that means HHVM loads all of the bytecode it may possibly need for serving the site. The alternative to this is to load it on demand. So when we render, say, someone's newsfeed, if we haven't already compiled that code, we'll fetch it and compile it and then render the newsfeed.
I see.
Cool. Thank you. Quick.
Hello.
Hi.
So how many commits per day do you have in the trunk?
Oh, how many commits per day in trunk? I actually have no idea. I would guess I don't know if it would be as many as thousands, but certainly hundreds, I would guess.
All right. And you said Facebook is a monolithic application. Do you have kind of roles for your PHP web servers? For example, feeds request goes to this bunch of servers, friends to this.
Right. Do we have homogeneous servers? Yes. At the moment, it's homogeneous. We just route requests to anywhere.
Cool.
That may change.
Just time for one more.
Hi there.
Hi.
You mentioned that developers have the option to request a merge, providing they're available to support. How do you handle the situation where a dev does that and then they can't be available? Health issues, family issues, etc.
So how do we handle merges without support, basically? So when you request a merge, requesting the merge is step one. Second is saying you're supporting your change, which means messaging an IRC bot. And then once to say I'm here to support, and then you have a certain window over which you're supporting. If that window does not overlap the next push, then we won't merge your request automatically. So if you're not there on IRC, then your code won't go out.
Okay, thanks.
Okay.
Great. So, Mr. Mark Drayton, thank you so much.
Thank you. Thanks.
So now we have Mateusz, who will speak about continuous integration for data center provisioning. So a big warm of applause, please.
Hi everyone, I'm Mateusz Kaczanowski, and I work as a production engineer at Cluster Infrastructure. Somewhere around 2 years ago, it happened that I was an intern at Cluster Ops in Menlo Park, California, and now I'm based in Dublin. So the question you might want to ask yourself is, why would I give up such a beautiful weather in favor of Irish weather? Beer. Yeah, beer is one answer. But to be honest, in my case, that was chocolate. So, as you may not know, chocolate in US is really crap. And I prefer that part of the world much better. So if you are really interested in a good chocolate, I would recommend you to go to Hotel Chocolate, which happens to be around the corner, and check it by yourself. But more seriously, as a production engineer, I'm responsible mostly for adding and removing capacity to and from the fleet. We are turning up internal core services. We manage typical internet services such as DNS, DHCP, NTP, or TFTP. And as a provisioning, we manage provisioning stack. Then that includes Anaconda, Chef, or bootloader, which in our case happened to be Grab2. Or also the orchestration that we've built on top of those standard services. Today I'm going to talk about provisioning and challenges related to data center provisioning space, but that really comes down to the question how to install that little guy on a single device. Or rather, I meant rack, cluster, data center, or even the POPs, all spread across the world. But while we're doing this, we need to keep in mind that at scale, number of elements that we need to take into consideration grows rapidly. Moreover, we cannot forget about the dependencies between those components unless we want to see provisioning broken. So the main question is the provisioning at Facebook really that different? Or more importantly, how did we end up with so many components and such complexity? To answer that question, let's take a look at our provisioning stack. So on top of well-known services such as DHCP, bootloader, Anaconda, TFTP, we've built our own automation, such as Cyborg, orchestration tool that schedules provisioning jobs, monitors the flow, runs different set of validation tools, and even checks the out-of-band accessibility. The other one is build control. That is a source of truth in provisioning world. It gives you information whether the host should boot from the network or the hard drive, or it's also responsible for generating kickstars based on our inventory system and imaging parameters. At high-level view, provisioning can be split into 3 stages: netboot, Anaconda, and Chef. So at first, when we power on machine, UEFI or BIOS sends DHCP request, where we respond with the address of TFTP server, so the machine is able to download the bootloader. After it's downloaded and executed, it fetches the configuration from the TFTP server again. Based on that configuration, we load the initRD and kernel, and after that, we are in a second stage, which is Anaconda, where the first thing we do is to partition the hard drive. After that, we install the base OS, and after that, we do some very basic configuration. After the host is rebooted, we run Chef, and that happens to be, in many cases, one of the longest parts in the provisioning pipeline. So it looks very simple. Where are the problems then? At first, we have hundreds of thousands of servers, and that translates directly into many hardware permutations, which we usually group by vendor model type. Where type describes the hardware configuration. So for instance, web host will be more CPU intensive, and the storage database host will require more storage or more RAM or faster storage. Our provisioning stack consists of many elements, such as Cyborg, Machine Checker, DHCP, TFTP, build control, Anaconda, or kickstars, and all of them are changing quite frequently. We support many firmware versions, such as BIOS or UEFI, or even the the firmware on the out-of-band chip. In some places, we rely on a third-party software too. We have customized partitioning with varied storage solutions, constantly changing kernels and inRDs, dual stack or IPv6 only clusters. We rely on out-of-band. If it's not accessible, we cannot simply power cycle the board remotely. Therefore, we cannot start provisioning. We have a few OS versions and lots of Chef cookbooks with many dependencies. And those are very tier specific. Therefore, from our perspective, it looks like a number of dependencies is pretty much indefinite. And at last, we have many data centers and POPs spread over the globe. So in that case, we need to take into consideration latency, especially if we are using such protocols such as TFTP. So the question you might want to ask now is, does it really work? Well, in case you didn't know, provisioning is a hands-free operation. So, so what I can tell you is that most of the time it works all the time, but a small percent of a huge number is still a huge number, and that generates lots of tasks for our own code. So not so far ago, we used to test everything in production. That means whenever you had a change, you landed a div, and build a new version, deployed it on production, it was very likely that you will see provisioning word broken. To prevent such issues, such as situations, we adopted the A/B testing model, where you have two provisioning stack, RC and stable. Each provisioning stack consists of almost all components that happens to be in a provisioning pipeline. And only difference between those two is that RC is is built more frequently. So if you take any host in production, any production host, and then you try to provision it with Cyborg, you may do it either through RC or stable, and that depends on the configuration. So A/B testing model enables you also to create your own customized provisioning stack, where all your local changes will be included, and then you can take a few production hosts and test them against your changes, so you will gain some more confidence before landing the div. So now we have RC and stable. The question is, how do we know when or if we can promote it or not. I mean, promote it RC. So each of the components in provisioning pipeline is tested somehow differently. For instance, build control and TFTP, those are Python services where we rely on unit test. On the other hand, Chef cookbooks have its own validation tools, and the same applies to kernel testing. So as you see, we are testing all of the components individually, but we don't test them all together. So in order to test the whole provisioning pipeline, we came up with CSP. That stands for Continuous Systems Provisioning Service, where the idea is fairly simple. We are just utilizing part of the spare capacity to perform our testing. And that is, we take a list of spare hosts, we group them by vendor model type and server network type, which might be either v4 or v6. Then we spawn provisioning jobs with Cyborg. And after that, we wait until the job is finished and store the result to database. Based on that data, we create alarming and monitoring. And also we have provisioning health dashboards. Oh, yeah, provisioning health dashboards. And at this very moment, we are testing RC and stable continuously. That means whenever there is an issue on RC, we can detect it almost immediately. But there is also another possibility for you to create your own provisioning stack, put it through CSP on demand. So after we deployed first version of CSP, we started getting significant amount of non-actionable alarms that were caused by noise in the data. So we started looking into it and looking for a possible cause and solution. At first, we found out that some of the out-of-bounds were not accessible. Therefore, we couldn't start provisioning. So in that case, as a provisioning team, we cannot do much. We can report the issue to the hardware team so they can fix the bug and possibly upgrade the firmware. Hardware fails all the time. That means, so in that case, we can either replace the hardware or exclude the sample from the equation, because replacing the hardware will take much more time. But then we might end up in a situation where we have too little of healthy hosts to determine whether a given hardware permutation is broken or it's not. So in that case, we can either increase the number of hosts or just adjust the monitoring to exclude data points where the number of machines is less than fixed minimum. In CSP, we set up provisioning timeout. That means whenever your provisioning job takes too much time, we cancel it and must mark it as failed. In some cases, it was really useful, as there were real issues where one of the provisioning components were taking too much time. But in the other cases, we were just too optimistic about the provisioning time, so we had to adjust it. And as we were utilizing part of the spare capacity, we need to be aware that it can be claimed at any time. So that means we can be in a situation where we used to have 100 hosts in permutation, and now we have 0. And obviously, this is not what we want. We want to test all of them as much as possible. So in that case, we fixed that, fix it by supplementing the spare pool with fixed capacity. After applying all of those improvements, our graph looks far better. It's not perfect. Some of the permutation are not being tested from a given point in time. And as I said before, in that case, we supplement it with the fixed capacity, so it's going to be visible on a different slide, different graph. With CSP, it's also very easy to detect failures, errors. For instance, we can observe trends, the red line, or we can see instant failures that might be caused by broken push or network issues. Whenever we need to promote RC to stable, we gain confidence by looking on the dashboards that this particular stack works well, so we can do it. Before the new model of hardware is being put into production, it goes through various steps of hardware validation. At some point, we put it through CSP to see whether the provisioning pipeline works well over there. We are also able to detect region-only or cluster-only level failures. We do test RC kernel, and of course we have broader view in what is going on with OOBs. So, have you ever had a bug that was really hard to find in production, randomly occurring in very different ways or affecting different hosts? I bet you did, and we did have it too. So I remember one particular case where a given permutation of hardware was failing due to some firmware bug after the hosts were provisioned X times in a row. And without CSP, this issue will be found probably in weeks. But with CSP, we have provisioning dashboards and well-formed data, so we can filter it out, narrow down the search area, and find the issue almost on the spot. So in the end, we've learned that flexible, therefore complex systems can be stable, and we don't need to sacrifice flexibility in favor of stability as long as we pay attention to metrics. So thank you for your attention, and if you have any questions, don't hesitate to ask.
So remember, you have the microphone right here. Keep an orderly queue.
Hello.
So many people.
Thanks for the talk. You mentioned Chef. Do you use any other configuration management tool?
So on a host side, after provisioning, we are using only Chef. I mean, it's easy. It's, we have everything in one place to configure. There are different tools some teams have their own way to rolling out things, but in most of the time, we prefer to use Chef.
Right. Another question, if I can.
Mm-hmm.
Do you daily test, like taking down a bunch of boxes just to see if the infrastructure reacts well?
Yeah, we do have this time of tests.
Daily?
Yeah.
Okay.
Maybe not daily, but anyway, let's say we have a significant amount of provisioning jobs in a day, so that gives us pretty much wider view what's happening over the fleet as we are using the host spread across the world. So if there is a problem with cluster or it's regional issues, then we can see it. Yeah.
Thank you.
Thank you.
Hey, do you have dedicated machines for each specific server, like for web server or database server, or do you install Docker and then run images, like more of them?
So we have 7 SKUs, as far as I know, and this is what I told as a type. So for instance, web host will have different type, and database host will have other type. I think we have somewhere around 7 SKUs, so yeah.
Have you considered using some containers so that you could have a physical machine running all web server and database and?
Yeah, I mean, we are trying to follow the CentOS. So in CentOS 7 there is a systemd, which is containerized system. So yeah, and we have our own scheduler, which is also containerizing things. Yeah.
Thank you.
You mentioned that you regularly test your various permutations using the excess inventory that you've got, and that if you run out of excess of a particular permutation, you just write it out of the tests. At what point do you write that permutation off completely and consider it dead?
I'm not sure if I understood the question, but so you're basically asking me, how do we make a decision whether the permutation is broken or not?
No. What you were saying was that when you test your permutations, you may encounter a situation where you don't have an excess of that permutation.
Oh, excess, you mean the hardware?
Yeah.
Okay.
And so you then write that out of the tests.
Yeah.
At what point, because clearly, obviously, if you can't test it, you may sooner or later end up with problems or with it becoming obsolete. At what point do you actually consider that permutation dead?
Yeah, so let's say we have a limit for 3 days. If a given permutation, and we care about this permutation, is not being tested because there was no hardware or someone claimed the capacity, we get the alarm, and there are tasks to specific persons to free for us the capacity as we need to test stuff. Yeah, so it doesn't happen I mean, usually it doesn't happen that a given permutation is not being tested. It is being tested.
Okay, so it's not just due to obsolescence then?
No.
Okay.
Question queue is full, so keep going on.
Hi, I wondered how long it was between discovering that you need more compute resource in a particular way and that actually arriving. Like, how long does your provision process take?
How long does our provision? So it depends on the machine how long it takes. But I'm not sure what you're asking.
So you keep a list of machines, right? Like a list of spare machines. And I heard you answer another question with like that you leave them there so that then you deploy them to whatever specific need that they have. I was wondering how quickly that can be ramped up. Could it, like, if you're in a particular period of one machine, one particular path through your code needing a lot of resource, like say if someone's posting a lot of threads into an event or something, somebody's creating a ton of events or something specific that requires.
So from our perspective, like the capacity engineering team, they do a very good job. So usually we have some spare capacity to use. And then it's like from my impression is that we use it for replacing the broken hardware. And sometimes in some cases, we are just simply need it to serve more people. But how often it happens? I cannot really tell you how often that happens. But yeah, there are some cases where like my graphs went down because all of the spares were taken, and I had to stay with the fixed capacity that we took. But anyhow, even 2 hosts failing in given permutation, it's a high signal. Especially if we use fixed capacity, we exclude the hardware issues because the hosts have to work all the time.
Okay, thanks.
Thank you.
We'll keep it coming. One question per person.
Hi there, thanks for the talk. If you needed to roll out configuration updates or just general updates across your whole data center, would you always use an immutable approach, as in destroy everything and recreate? Or is there any times you would use like convergence, like chef idempotency, things like that?
Depends what configuration. If you want to know more about rolling out and how do we roll out configuration changes, I would rather ask Mark. But from the infrastructure point of view, yeah, I mean, depends. If it's after hosted provision, what happens after hosted provision, it's probably not my case. So, so I know what happens till the hosted provision.
Okay, cool.
Okay.
Hi, thanks for the talk. What steps are taken in your data center until a RAG or a pod is ready to run the cyborg?
So you're asking what are the steps before we provision the machine, yeah?
Yeah.
Yeah, okay. So so first RAG comes in, the network guys come in, connect the cables, and after that we put the host into our inventory system, and based on that data, we know there are different statuses. So whenever they're working, I mean, the network guys are working on the machine, we know about it. But after that, usually machines have some purpose. So as a cluster infrastructure team, we turn them up, and that means after the host is provisioned, we start the internal core services that are required to start other services and support our product owners. I mean, products.
And another one, how do you test? Do you use the chef tools to test, or do you have your own? And how do you narrow down to the component that has a problem?
Oh, so yeah, that's the CSP right now. But in general, when there is an issue, the cyborg, which is the provisioning orchestrator, tells you, okay, there is an issue, I cannot provision the box, and usually we need to take care of it.
Thanks.
Okay, thank you.
Hi there, thank you for the talk. I'm mostly curious about the process you use for releasing cookbooks. What happens from the developer up to the moment it's on the machine and ready to provision it?
Okay, so after developer changes something in a cookbook, it goes through some validation process. I mean, so I'm not the chef guy. We are managing chef, but from my perspective, before we deploy something, I mean, land the chef cookbook div, then it's gonna be tested on a particular host, and there is some automation behind that. It's also testing the chef divs.
Is that in-house or open source projects?
It's in-house. Yeah, but we are also there is a field D here, so I think he's the chef guy. He can tell you much more about it than I.
Do you guys use the system for provisioning any Windows hosts, or do you have any Windows hosts? And do you use any kind of similar systems for imaging workstations or any?
I don't know. Seriously, I'm not that long in Facebook, and from my perspective, we have only CentOS, and this is what I care about. So maybe there is, but I don't know. Yeah, sorry.
You mentioned a lot of problems and provisioning steps come from having multiple hardware types and different vendors, etc. What's Facebook's view on moving towards a standard type of build, or along the Open Compute platform, or sticking with a single hardware vendor? Or
as far as I know, our hardware is an Open Compute, so whatever we use, it's there on OpenCompute.org. Yeah, I didn't get the question, sorry.
Just because you mentioned a lot of problems and the provisioning steps come from having multiple hardware types and different vendors.
Yeah.
What's the view of moving towards a...
So, like, our clusters live for some time, and let's say after this time expires, the clusters goes out. So whenever we are introducing new model of hardware to production, we get the new clusters with the new hardware, but the old one stays. So it's like a long tail. And then after some time, they go out, but still in some places, we'll have some of them. So the window area where we have X number of permutations will always belong, as some will go and some will be added and some will go.
Cool.
Yeah.
Hi. If you're allowed to tell us, how many servers would you run? What's the failure rate, and what's the delta? Like, how many new servers would you provision, like, per day, for example?
So we have hundreds of thousands of servers. That's what I can tell you. The second question was?
What's the kind of failure rate, and how many new servers might you provision? I mean, is this ever increasing?
So it depends. I mean, it's really hard to say why it fails. I mean, what is the failure rate or on each of error codes, because it might be hardware, it might be network, or it might be someone's div who broke the stuff and it still doesn't work. So from our perspective, it looks like, yeah, okay, there was a div. And we have plenty of statuses, plenty of error codes that will indicate what was the issue, some part of the granularity. So we will not waste time for checking it manually where actually Anaconda got stuck. So I don't know answer for that question. I can tell you that.
So in terms of provisioning,
yeah.
I mean, any ideas like how many new servers you'll be adding every day?
How many servers we are adding? It's not every day. Usually when we turn up stuff, then we turn up cluster, and it's a logical unit. It consists of thousands of servers. They might be added to the data center, but they will be not used until we turn up the cluster, because otherwise no one can start, let's say, their service on a cluster. Yeah.
Cool. Thank you.
What's the minimum of a particular permutation you test on before pushing it out to production?
So it depends. We have, let's say we have some X permutations. So what we care the most is that, let's say, 120 of them, or 100 of them, or 1,000 of them, I cannot tell you, but some amount of them will work. The other ones, it depends how many hosts in a whole fleet we have, and that is, usually everything should work, but sometimes it's, yeah, we can fix it later, or it's pretty much broken, we should fix it right now.
Okay, brilliant, thanks.
Okay, thank you.
Thank you very much, Matthias, for your...
Thank you.
Thank you.
Okay, so on to our third and final talk of the evening. Very privileged to have Docker Captain Elton Stoneman here. Captain, my captain, coming to the stage. He's going to talk about Docker and IoT and some disasters. We like hearing about disasters. All yours, Elton. Elton Stoneman.
Thank you. Okay, cool. So, IoT, DevOps, and Docker. What a fantastic time to work in IT. So my name's Elton. I've been delivering software for a lot of years. I've accrued some interesting titles along the way. So I'm a Docker captain. I'm a Pluralsight author. I'm a Microsoft MVP. Now, not everyone's going to like that, so I've written it a little bit smaller, just so to show that I'm in sympathy with the crowd. So I'm going to talk about a project that I was involved in for 2 years, building out the back-end services to support a whole suite of mobile devices. An IoT roadmap, actually, that was going to be a cornerstone of a company's strategy. And as you'll have guessed from the topic of the title of the talk, that didn't work out so well. We got a little way down the line and the project got canned. But actually, there's still some interesting learning points about how you can do DevOps in an existing organization, and some of the challenges you face, and how we got around that using the latest sets of tools. So the story of the project kind of fits neatly into 4 phases, which I'll go through them in that order. So to start with, there was the burn, then there was Christmas, then there was the crash, and then finally there was the rebuild. It's all quite melodramatic, but this is actually how it happened, apart from we didn't have Alan Titchmarsh there. But I do live in the same village as Alan Titchmarsh. So a tiny bit of background. I joined the company just after they'd released their first device, which was an Android tablet. They'd sold 700,000, and they were just starting to work on the second generation, which was also an Android tablet, and that was slated to sell 1 million units. The company was a retailer, a grocery retailer, and the CEO had a kind of broad strategy of how to expand beyond the grocery realm, because it's quite a narrow market there. So they had an online content platform which they were building out. And the devices were meant to be the kind of glue between those 2 parts of the company. So you might only go into the shops 1 day a week for your groceries, but the other 6 days a week you'd be using your devices to read the ebooks and consume the streaming music services, watch the TV and the films. So we were a central part of making that strategy happen. And in this sort of project, if you're building a device from scratch, it wasn't an off-the-shelf device that was repackaged, it was built to order. The key date that the team is working towards to start with is the burn date. Now, that's the day when the devices started being made in the factory. And you have to get a lot of stuff ready for the burn date, because it's called the burn date because the operating system is burnt onto the ROM, it's burnt onto the chips, so you have to have an operating system. You have to have the apps that are going to be consuming your content at least ready in some form, and you have to have the back-end services. You at least have to have the contracts ready so that you know your firmware and your apps can talk to those services. And the burn date is way before the product release date, like 6 months before. So you've got a very short amount of time to deliver a lot of software, and it has to be pretty high quality. So this was a fairly well-established enterprise organization with a big established IT group. And if you've worked in those sorts of operations, and Facebook might be an exception, they're not very good at delivering high-quality software in a very short time frame. They're built around delivering website updates 2 or 3 times a year, and then spending a week or so tidying up after the release. And they were well aware, to their credit, they were well aware that their existing structures weren't going to enable them to deliver all this stuff quickly. So they spun up a completely separate team. So the device team had their own office space where all the business people, the hardware people, the software people all worked together. And we were isolated from the rest of the organization. And because we were a new team, kind of hand-picked, we started doing things the right way. We didn't have a whole lot of legacy stuff to support, so we started with all the processes that you'll have heard about from these sorts of sessions. We didn't have separate devs and ops people. We had a whole bunch of tasks to do, and whoever was the right person to do it, did it, starting with building up our pipelines. So we had our central source code. We had Jenkins for all the different types of software we were building, and then for each pipeline, whenever you checked something in that was a device driver update or a change to the app or a change to the service, it would trigger a build and it would push it out. because we had our own space, we could do some funky things. So we had various Wi-Fi networks in the office, and each of those was hooked up to a different slice of the services. So if you wanted to use the latest build, you connect your device to Muffin, and every time there was a new push, you do an update and you get the latest version of the apps connecting to the latest version of the services. The nightly build, you connect to Brownie, and then you'd have a stable build all day. So we owned all that stuff. We could do everything we needed to do because we owned all the cloud accounts for Azure and AWS and Rackspace, and we used them all. We owned our own infrastructure inside the office, and we took care of all that stuff. And it turned out when we tried to interact with the main organization, they weren't really geared up to supporting us. So if we needed a new domain for our APIs, if we were flexing the way that we were striping our services, we could put in a ticket, but it would take 10 days for us to get a CNAME set up. If we wanted to secure it, there was a chargeback of £2,000 for an SSL cert, and it would take 10 days to get that as well. So for production, you can kind of live with that because you're only going to you have a window where you know you're going to release, and you can get all your requests ready in advance. But when you're iterating fast in a dev and test environment, you can't do that stuff. So to get around that, and because we owned our own little domain, we created our own domain name for non-production environments. We had our own wildcard SSL cert, and anyone who needed to spin up a new domain had the authority to do it, and we did it ourselves. Because of that, we were able to move fast. So that left us with all our own infrastructure, all our own cloud accounts, our own domain. We were effectively a rogue unit that wasn't using anything that was approved or supported by the main organization. Big enterprises don't really like that. So we had to do that so that we were enabled to move and to deliver this stuff. But obviously the main enterprise was kind of not happy with that. And this was the first learning that we had from the early part of the project when we were getting ourselves geared up for the burn date, was that we needed someone who could keep those realms apart. That's meant to be Atlas, the Greek guy. So we were extremely lucky that the program manager of the device team was someone who was powerful within the organization and respected by the main enterprise. So he was able to keep us separate. So all the requests for red tape and form filling and anything that would have slowed us down, any meeting requests were just canned. Everything went through him, and he stopped everything. And it wasn't until much later in the project, when he moved on and we didn't really have a replacement, that all the bits of red tape started to come in and slow us down. We realized what a good job that guy had done. So when you're talking to people who have done DevOps and tried to integrate it to an existing enterprise, the consensus is that you want to start with a small project. It's going to be driven from the bottom up, from the engineers and the ops who are actually going to be doing this stuff. They need to be enthused, but it has to have support from the top down as well to make it happen. And from my experience, I'd go a little bit further with that. I don't think it needs to be a small project, but it does need to be contained. So we had quite a lot to do, but it was clearly delineated. So it was clear what we were doing and how well we were progressing. Infusing from the bottom down is a must, but the guy from the top can't just be someone who says, this has my blessing. It needs to be someone who's a gatekeeper. If you're trying to operate a separate silo within a larger organization, you need someone who can keep that silo working effectively. So up to the burn date, we were working hard. And by the time the first devices were being built, we had our first version of the firmware, first version of the apps and the services, and it was all good enough to ship. And the first consignment of devices, we siphoned about 200 or 300 of them and distributed them around the organization for early adopters, who are going to be our beta team. So from that point on, when we're doing our iterations and our multiple releases, we were releasing to production. The devices weren't on sale yet, so people weren't actually using them, but all the early adopters weren't in our office using our Muffin and Brownie networks. They were at home, so we were releasing to production every day to make sure they had the latest updates. With all the services, all the apps, all the different parts of the firmware, we had over a dozen products, but we had a single backlog where anyone who was interested could go and see what was happening, what was coming in the next app release, the next service release, and if they were interested in what had just come out, they could update the device from home and get the latest versions. So we were working towards the next milestone now, which was Christmas, because it's a retail operation. Christmas is a big deal. by early December, we were pretty much feature ready for our big cut to our major release, major delivery. We had all our monitoring in place for the devices, so we knew how well they were working, and we could tell if there was a problem with if we did a firmware release that destroyed battery life, we would know about that quite quickly. And we had monitoring for our services, so we knew that all that stuff was up and all running correctly. We'd done a whole suite of performance testing, so we knew that the services could cope with a lot of load, which they needed to do because we also had stats from the business who told us how many devices had been sold. And in the run-up to December, we had 300,000 devices that had been sold and not activated. So they were hidden in lofts and in cellars, and they were going to come out on Christmas Eve and go underneath thousands of trees and all be turned on at the same time. So we had to be sure that our services were going to scale to support that sudden spike in load. So those services, some of them were pretty crucial for the unboxing experience when you turn your device on. And the first one was the device API. We didn't spend too much time with fancy names. So the device API, periodically the tablet would call home to the API. It would say, I'm running version X of the firmware. Is that the latest one? And the API responds and it says, yes, it is. You're fine. Or it says, no, there's a later version. You need to download it from this URL, which takes you to a CDN. Download your 400 megabyte file or your gigabyte file, and then run your install process. And that was pretty critical because we did it periodically during the life of the device, and if the API failed or the download failed, that's not a big deal because it'll try again later. But for the unboxing, because it could be, when you open your brand new device, it might have been made 6 months ago with a version of the firmware that's 10 versions old. When you unbox the device, this is a mandatory step. So if the device can't talk to the API or it can't download the upgrade, you can't do anything with it. You're just sat there looking at a paperweight and wondering what you're going to do with what's next under the tree. To support that, we had a nice fancy little UI. So anyone in the team who had the authority could go and put in all the details for a firmware update, click the button, push it out to production, and then the next time any device called in to check, it would get the latest download. The other key service was the monitoring API. So these devices, like all the devices in your pockets and your bags, are monitoring every single thing you do all the time. So if you turn it from landscape to portrait, it logs an event. You plug in your headphones, you change a different Wi-Fi network, you lock onto GPS, you plug in your charger, you unplug your charger. Every single one of those is an event. And the device logs them, stores them locally, and periodically pushes them up to our central API. And we collect all that stuff. And we had an analytics platform to try and make some sense of it. So anyone who's kind of big data in the room, you'll recognize there's a standard pattern for dealing with that data. So some of it went through the hot stream and was surfaced in real-time dashboards, and the rest of it, all of it was stored permanently, and we could run a whole bunch of Hadoop queries to get more complex information out. And all that information went into a centralized set of reports that was used by the product team. So those guys who were building and designing the Generation 3 device and all the other things that were coming were using being informed by the user stats to work out what to do next. So if you know that your device is predominantly used in landscape, then the next one's going to be a landscape device. If you know it's always plugged in, then either you need a bigger battery or you need a smaller battery because people are always plugging it in. But at least we had the stats to back up their designs and make the next set of devices more attractive. So all this stuff was in place. We'd done all the feature testing, all the performance testing. We were happy that it was all good to go. And the last real test to do before Christmas was to do our capacity planning. So the capacity planning task came to me because I'm the Azure MVP and I've done all this stuff before and I know what I'm doing. So I went through all the key services and worked out what we needed to do and got everything scaled up on Christmas Eve, so it was all ready in advance for Christmas Day. So knew how many cores we'd need, how big the message bus needed to be. For the CDN, all the limits were clearly specified, so made sure we were in the tolerance, and it was all looking good. And so went home at lunchtime on Christmas Eve, safe in the knowledge that I'd done half a day's work and I was going to get a full day's pay, and looking forward to the Christmas break. But unfortunately, I made a mistake. And I found that out Christmas morning when I got a call from the program manager, the Atlas guy. nice guy, and we got on well, but not so well that he's going to ring me on Christmas morning to ask how I'm doing. So this is DevOps. You build it, you run it, so effectively I'm on support. And I do what I guess anyone would do if you get a phone call on Christmas morning and you're on support. I picked up the phone and said, ho, 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 Merry Christmas, in a kind of transparent attempt to defuse whatever situation was about to come my way. And there was a situation. As well as all the 300,000 people who were going to be turning their devices on, we had automated tests that were checking the kind of unboxing process, calling the API, making sure they got the right response, and then trying to download the upgrade and making sure that they could get the file. And one of our tests was flickering. So the API responses were all okay. So I went through, and we had the same set of tools that we could run manually to check the API as were being used for all the automated tests. So ran that through, it was all fine. Lots of responses, all positive, all sub-seconds, so that was working as expected. Checked the download URL, and that was okay, and I checked it again, it was okay, and I checked it again, and it failed. And so I went over to the Azure portal. It's Christmas morning, by the way. I've got my glass of Bailey's, so it's not the end of the world. And the Azure portal was telling us that the downloads were being throttled. So effectively, we were hitting one of the limits that I thought we had plenty of tolerance for. So I'd made a mistake, but I know what I'm doing. And so we had a DR environment for our core services, not for everything. We didn't need disaster recovery for the analytics platform or anything like that. This is proper, separate cloud. If there's a problem with Azure, we need to be able to keep running and keep the devices working. Called it the minimum viable disaster recovery environment. And it paid dividends because the APIs were working fine on Azure, didn't need to change them. All I needed to do was redirect the download URL to use our Rackspace CDN, which had a different way of working with limits, and that was all fine. So when I was thinking about this and thinking about the kind of lessons learned, I first thought that the lesson from this experience was DevOps is great. The people who build the software, support the software, they can zone straight in when there's a problem, and they can fix it correctly and quickly. But on reflection, I don't think that is the lesson. The lesson is that I made a mistake. Well, I'm partially human, so that's to be expected, but I didn't make my findings from my calculation process available for the rest of the team to inspect. And actually, I needed to be a bit more like this guy, the naked rambler who, other than his frequent spells in jail, has got nothing to hide apart from whatever's in that rucksack. So I'm not suggesting that you need a more relaxed dress policy or anything like that. I'm saying for DevOps, then for it to work, it's the team that either succeeds or fails. And you need a lot more openness than you would previously have had. So I'm used to kind of working in an environment where there are subject matter experts that have key parts of knowledge that they know how to do certain things, and they're responsible for certain decisions. But actually, in the DevOps way of doing things, those guys aren't really an asset now. They're a liability because the rest of the team can't work unless that person is available to help or make decisions or whatever. So for you to be able to work properly in this way, you need to have a lot more openness, you need to have a lot more discussion. Pretty much any decision is going to benefit from an extra pair of eyes, provided getting the eyes onto it doesn't slow you down. So in the new year, we got past the Christmas thing. So we had sort of 10, 15 minutes of potential downtime. We didn't actually impact any customers. We got it all working again. So in the new year, we got Microsoft in, and we did a post-mortem, and they had all the stats to prove it was definitely my fault. So we said thank you, goodbye, and we moved on. And the next stage we were interested in was the next set of devices. We had some prototypes made for the phone, and they were like this. They were like the old trigger-happy TV phones, so that went back to the drawing board. And on the services team, we were more interested in the next computing device, which was going to be a Windows convertible tablet thing. So different operating system, different set of events that it could capture, and we were trying to work out what we could get from it that would allow us to reuse as much of our existing APIs as possible and make sure that no matter what device you were looking at, you could use the same querying tools to understand how they were working. So we were investing our time in that. Time spent wisely, apart from we soon hit this crash. Extra t-shirt for anyone who knows what film that is, by the way. You can tell me at the end. So the quarterly results came through, and they were not good to the extent that it was patently apparent that the retail plus digital platform strategy just wasn't working. And the CEO got kicked out, and a new CEO came in, and he looked at it and said, nah, we're not doing this anymore. So we'd gone in the device team from being the core that held the strategy together to being this slightly strange outlier with a big grocery retailer who had a device roadmap that didn't really fit in anywhere. So obviously the roadmap got canned, and then we were even more of a strange outlier because we had a grocery retailer with these two devices that we had all this software to support. Now, when we had the whole roadmap, and we were going to be doing this for several years, and some of the guys were looking at home automation, fitness, nutrition devices, interesting devices, 4 or 5 years down the line, having all this stuff running was okay. It cost about 30 grand a month in our Azure fees, but we were actually giving value to the business because we were definitively helping them to design the next set of devices, make them more attractive, and make them more saleable. But obviously, everything had changed, so all this stuff we had wasn't really giving much value anymore. And although we'd built everything the business wanted us to build, it turns out we'd kind of built this thing, which is the boat car thing that no one actually really wants. So we put all our time and effort into building a really good solution, and we had all the processes to make it happen in a short amount of time with a high degree of quality, but it wasn't needed anymore. So what the business wanted to do was just turn everything off, which would have been fairly easy. We can just shut down the Azure account, everything ends, bill goes down to 0. But we couldn't really say what was going to happen to the devices. Because although the apps and the bits of firmware that were hooking into the services were well written and they were fault tolerant, they were tolerant for transient faults. If the services weren't available, then they would try again a little bit later on. If the monitoring API wasn't available, then the device would have had a rolling log, so it wouldn't use up all the memory. It would start again if it reached a maximum. But we'd only tested it for transient faults. We didn't know how it was going to react if all those services disappeared forever, because these are mobile devices. They're meant to talk to a centralized service. So we had to try and work out how we could take all our complex and expensive software and get most of the functionality for a fraction of the money. And so we entered the rebuild phase. We spent a lot of time looking at what we had and arguing about what we could keep. Maybe if we scaled those down by a few servers and scaled that up a bit and changed this a bit. And actually we spent way too much time trying to work out what we could salvage from all the stuff we'd built. And eventually we decided that actually we need to approach it from the other way. We need to look at what the devices need and build the services to support that and that alone, and look at what the business need in terms of statistics. They still wanted to see how many devices were being used each day, how many versions of, for each of the versions of the firmware, how many devices had them installed. They wanted some stats. But we had to effectively rebuild what we had. And the guiding principles for that phase were we had to deliver quickly because the team was disappearing. When your product roadmap gets cancelled, then most of the people kind of move off to do other things. And fortunately, everyone went off to do bigger and better things, so there wasn't a human cost to this. It had to run cheaply because that's the overriding requirement. There's got to be something that we can say to the business, it's now costing X, and that's okay. We can run that, indefinitely. And there had to be a very small amount of software to support, because once the next kind of set of releases had been done, the team was going to be wound up. There wasn't going to be anyone involved in the project left in the company. And we'd be handing it over to a support team, and we didn't have the luxury of 2-week handover or 3-week handover. We had to have as little custom code as possible. So we had this, and most of it wasn't going to be usable anymore. So we started to think about how we could take the key parts of it and re-architect it using existing components, using Docker to give us the core parts of the new architecture and just have a thin layer on top, which was our customizations. We'd already been looking at Docker for our tool chain before it all sort of went bad. And we were getting a lot of experience in how you could use it and what benefits it gave you. And by the time we hit the point where we had to re-architect, the Docker ecosystem had matured to a point where it was something you could run a swarm in production. The Docker machine was integrated with Azure in a way that we could make sense of and use. And the official images on the repository on the Docker hub, there was some really high quality stuff out there that we could take and use and start using straight away. So in about a week, just over a week, we put this together, which was the new architecture. For all the expensive parts of the existing architecture got thrown away and rebuilt using this. So this is how it's hosted at the moment. We've got a handful of nodes that are all part of a single Docker swarm running up in Azure, and they're partitioned based on whether they need to be accessible to the outside world or just within the swarm. All those APIs, which were originally .NET complex APIs that were dynamic, so every time we got a request from a device, we did a whole lot of logic to work out what response to send. We threw all that away, and we had static websites in Nginx. So we took the JSON responses for all of the paths through for the GET requests, captured them in documents, and ran them in Nginx. So as far as the devices were concerned, they had exactly the same contract. Whenever they did a GET request, they got exactly what they were expecting back, but it wasn't dynamic. It was coming from a website. It just happened to be JSON rather than HTML. Anytime they posted information up to us, which some of the apps did to capture what people were doing, other than the monitoring, for those apps, when they sent up a post, we just ignored it. So we sent back the response they expected, 200 or 201, and then we just threw the data away, because we didn't need it anymore, so there was no point having it. But we couldn't change the contract without updating 1 million devices. And the other expensive part was the analytics platform. So we had all that stuff with the real-time dashboards. We had SQL Server. At one point, we were using HBase and Storm. We had Hadoop in there for the longer-running queries, and we threw all that away, and we replaced it with Elasticsearch and Kibana. Again, those have official images on the Docker Hub. You don't even need to write anything for those. You just pull them down and configure them so they can talk to each other. Had to write a small component to pull from the existing device monitoring API and push it into Elasticsearch, but that's like 20 lines of code, and have that running on a negligible amount of hardware. So some of the things we left as they were. So the CDN, there's no point replacing that. We know that works. But other than the Christmas issue, it did fundamentally do what we needed to do. The monitoring API that the devices send up their batch of events, quite a lot of complex stuff going on, but not an expensive run rate in terms of the number of cores it needed. So we left that as it was. Only the things that were expensive we rebuilt. And the run rate overall with this and the other bits now is about 2K. So we've got it down considerably. And more importantly than getting the cost down is the amount of code that we had to write and then support and maintain, which was next to nothing with the new way of doing things. We didn't have a whole bunch of services that were running that had hundreds of thousands of lines of code. We just had hard-coded, effectively JSON responses for our Nginx websites. And in terms of deploying this stuff and building it, we just had a handful of Docker files, Docker Compose file, some PowerShell scripts to spin up the whole environment, and it's a portable environment. So if we need to move to another supplier or move it in-house, we just create the swarm and run up the containers there. Which kind of begs the question, given that we did this in just over a week, why did we spend 18 months building all this rubbish? And there's a whole host of answers to that. The first one is we kind of had to, because a lot more stuff went on in the first release of the software, things that we didn't need to do once the program had wound down. Secondly, we didn't really have any choice, because all this being able to pick containers off the shelf and build up your solution with a minimum amount of custom code wasn't really available back in 2014, an awfully long time ago. So we couldn't really have built it in the way that we did by the end of the project anyway. And that's the kind of final lesson. So the era of Docker and the application container is not just about making things easier to build, ship, and run. I think it also should affect your solution design right from the beginning. So instead of building your own code, you should be picking things off the shelf. Things that are open source, tried and tested, used all around the world, and maintained by the people who build it. So you can take that and just put your thin layer on top. So you're focusing in on what your business actually needs to deliver, and you're giving them value without building up a whole big stack of custom code. Help you deliver better software more quickly, which is what I think the essence of the promise of DevOps is. So that's my cut out and keep guide to how to do kind of DevOps and IoT and Docker. You are going to need someone to support your team if you're trying to do it inside a larger enterprise. And that person's going to need to have to keep the teams isolated from all the negative slowing down that's going to happen from the enterprise. the team needs to be open and work together, because otherwise you end up with experts who are going to ultimately slow you down because they're not always going to be available. If you find yourself building something that no one wants, get over it as quickly as possible, throw it away, and concentrate on building something that people do want. And when you do that, take as much as you can off the shelf, and don't build a lot of custom software if you can avoid it. And that's that. So obviously I'll be taking questions. I mentioned that I sometimes make mistakes. I got in touch with Pluralsight, and they sent me a big stack of 1 month free passes, which I left in the office. So I haven't got any of those. But if you're really interested, then ping me or see me at a later meeting. I'll have some, and I can get you hooked up with those. There we go.
Thank you, Elton. We have more food getting ready, so time for 4 questions. Yeah, make it quick so we can get food.
Hello,
Hi.
it's Spitz. You mentioned Docker Compose. My question is, basically it has 2 parts. First of all, where did you deploy the containers? And second of all, how?
So we deployed them in Azure. So we created the infrastructure in advance. So we use PowerShell scripts to create our virtual network and our subnets in between. We use Docker Machine to actually create the VMs and put them into the right subnet, either for public access or internal access. And then with Docker Compose, we were saying, here's my Nginx container. It has to run in a machine that's flagged as public. And so when you spin that up and do Docker Compose up, it will put it in the right slot in the swarm, because I've tagged it to say this container has to run on a VM that's got a public label, or for Elasticsearch, it has to run on a container that's labeled as internal and very big hard disk. So those guys went to machines that were beefed up on the storage side. So yeah, it was all done through scripting.
You didn't use Jenkins at all, and Jenkins job to...
No, not for the rebuild. So by the time we came to do the Docker stuff, the team had kind of shrunk down to me and 2 testers. We had a couple of weeks to get it done, so we didn't bother with any of the deployment stuff. We didn't bother with the big pipeline. We wrote everything in scripts, so in theory, if the project ever got resurrected, then they could use those scripts as part of that pipeline. But for what we had, no.
Cheers, thank you.
Okay, thanks.
Hi. Would you have considered changing your cloud provider if Microsoft didn't have Docker?
Good question. Yeah, we probably would have done. Yeah. So for the re-architecture, one of the main things was to make it portable. So we could run that whole stack on the laptop, get it all working, and then just push it out there. We had arrangements with AWS and Rackspace. So anyone who could give us something that we could run Docker, we would have gone to. But Microsoft do let you do Docker. Thank you.
Just 2 questions. So first one. How long did it take you to do the rebuild? First question. Second question is, was the cost saving down to the rebuild, or purely down to rebuild, obviously to move to the Docker as well?
So the first question, how long did it take? Well, for each of the APIs, it was a question of I should have said actually. So the technical details I've blogged about, so you can check me up on my blog. There's more information there. For the rebuild, each of the APIs, we were looking at working out if the responses were generic to every device. So that was easy, just capture the JSON. If the responses could be made generic to every device, same deal, just capture the JSON. Or if they weren't really applicable, then we had to work out what to do with that. But each API, we're only talking about a couple of dozen responses, so they're probably taking about a day each to do that. And then the analytics platform side of it, setting up and configuring a handful of Elasticsearch nodes and plugging in Kibana and setting up they're only interested in sort of 3 or 4 real metrics, headline metrics. That was only a couple of days. So the final part of that, the scripts to put it all together and push it all up to Azure, again, probably 2 days. So I would say between 6-7 working days to get that done. The cost savings were primarily because we were using an awful lot less compute. So for the first version of the architecture, where we had, an Hadoop cluster is going to use a couple of dozen CPU cores, and for our APIs, we had autoscale, but even the low level was using kind of 50 or 60 cores, and it would scale up to kind of 80, 90 depending on the load. So getting rid of all that and replacing it with the Docker stuff meant we're literally running on less than 20 CPU cores for the whole thing now. One of the main reasons for that is because Nginx is so highly performant. So we can run that on a really low performance node, and it will still serve 2,000 requests per second. So,
Thanks.
All right.
Hi there. I'll just go for the film, Trading Places.
Yes, absolutely. Extra T-shirt, please.
This is the last question.
Thanks for a fascinating talk. Going back from the unpredictable event to the predictable event, was there any account taken in the device design of the Christmas out-of-box experience as against the server design?
Yeah, good question. So there was an ongoing discussion for pretty much the whole length of the project before I joined, and probably still going on now in a pub somewhere, as to whether we should have this hard dependency on the device API for the unboxing process. And actually, there was no need for us to technically have to do it. So we could have had a version of the ROM that was sufficiently capable that we could burn it right from the burn date. Oh, I pushed a button. Sorry. But practically, if you're going to go to your product team and say everything needs to be ready 6 months before we're going to ship, they're not going to have it. So the mechanism there was to give us effectively 6-month window to develop more features. So it wasn't a technical requirement, but it was kind of a business requirement. Okay.
Thank you very much, Elton.
Okay. Thanks.
Okay, and we're about finished for tonight. The last thing that remains is this glamorous cardboard box I've got. It's time for the world famous London DevOps paperweights. Hooray! Hey, cool. So if we can just call our speakers back onto the stage, please. Mark, are you around somewhere? Cool. And Matthias and Elton? Cool. Here we go. Just have one last big round of applause for our speakers. Thanks very much, guys. And the famous paperweights is one for Mr. Drayton. I think you've got two now. Hey. And some bubble wrap to put it in when you dump it in the bin outside. You still have it. I'm glad you still have it. No, seriously, we give you these out because speakers put in a lot of effort, a lot of time and come and stand in front of you lot and answer all sorts of intimidating questions. So we really do appreciate the time that you guys put into it. So thank you. The next one is for Matthias. Yep, that's the right one. There you go. And finally, and I think, Elton, you've already got one from WinOps, right? You got a similar one, not quite the same. So, where is it? This is brilliantly prepared, isn't it? Can you help me, Mark, please? Elton Stoneman, thank you very much. Right, that's everything. We've got there's some more food, hooray, and some drink out here. Also, there's some T-shirts left over, so if you want a T-shirt, then try not to all run at once. Can you collect up the bottles and stuff and put them in the recyc, if you wouldn't mind, just so we don't have any accidents. That's about it. Next meetup's in 2 weeks' time, Cloud and DevOps World Forum. Thanks for coming. Hope you enjoyed it. Goodbye.